What is cosine of omega t plus pi over 2? Becomes just minus sine of omega t. Okay, some of you are quite speedy. You can go directly from here to here. Okay, if you're not speedy, then I can go through the details. And those are the maths that you have to go through to go from here to here. Okay, I don't mind going through the math, but so the other one, we get BC to be negative of that. We get BC to be negative of BL is minus J 1 over R square root of LC. That is my BC. In order to convert this into a time domain quantity, I go through the same operation, BC e to the j omega t. And then I will get real of 1 over R square root of LC. And then minus j, if I express it in polar form, what does it become? Negative of pi over 2, and then j omega t, right? And then now if I take the real part of this, what do I get? Remember that this can be consolidated. J omega t minus pi over 2. Okay? This can be consolidated into 1. This can also be consolidated into 1 by using one of the formulas. So if you take the real part of this, what do you get now? You just get sine of omega t. Okay? Sine of omega t. So are there any other questions regarding this? So if there are no questions, maybe we can recapitulate what we have learned today. We learned that if you have an inductor together with a capacitor, it can look like a short circuit at omega equal to omega naught. And omega naught is a resonance. Omega naught is equal to 1 over square root of LC. Okay? And then if you have this connected in parallel with a C and L, okay? And it can look like a, what does it look like at resonance? It looks like an open circuit. Okay, it looks like an open circuit at omega equal to omega naught equal to 1 over LC. It becomes an open circuit. This becomes a short circuit. Okay? And then if you drive this system can sustain itself without any driving force. Because it's a resonance system, it can be current flowing there without any driving source. If you were to further drive the system, and if you have no loss in the system, the amplitude of the voltage can go to infinity. So it's very important that you do not design an electronic system with resonance in it. What happens if you have an electronic system with resonance in it? It goes haywire, right? And you probably have experienced that as well. If you have a microphone, if you are talking about a microphone and then the microphone gives out a voice in the hall and the voice feeds back into your microphone, you can have a resonance system. Okay, you have a resonance system and then the whole amplifier can go to a very loud or high pitch, right? And those are called resonances. So actually I'm just asked to talk about this, I think, nothing more. I'm just asked to talk about resonances. In this lecture. So I can move on to what I'm going to talk about tomorrow, or I can revise things with you. Which one do you prefer, revision or moving ahead? Yes? Moving ahead. So why don't we just move ahead then? Since I don't know why I'm given so much time to talk about this topic. Okay, let me talk about what happens a frequency response. So, if we have an input signal, f of t, okay, we have output. Output, sometimes we call it v of t or I of t. It depends on what kind of circuit we are solving. And then in the phasor world, or in the frequency domain, we often just call this f of omega. And then in the phasor world, we can just call this output v of omega. If the output is a current, usually we just call it I of omega. Okay? The frequency response h of omega is defined as such. The frequency response is the ratio of output in the frequency domain divided by the input in the frequency domain. Okay, that is the definition of the frequency response. And in this case, it will be, in one case, it could be v of omega over f of omega. Okay, that is the frequency response. This frequency response is given different names. Sometimes it's called transfer function. Okay, and this is very useful to defining linear time invariant systems that you have been studying, LTI systems. Let's do some examples as to what this frequency response is. So if we have a phasor circuit, like example 5.1, if we have a phasor circuit with an input Vi to be my input, and then I have a resistor R, and then I have a capacitor over here, C, and then I take this to be my output, V out. Okay? How do I write V out in terms of Vi using a phasor circuit? If I use this to find V out using a phasor circuit, which formula comes to your mind first? Which formula comes to your mind? KVL, yeah, that's about correct. Voltage divider, very good. Voltage divider, right? Voltage divider V out is just equal to the impedance of this, which is j omega c divided by the total impedance. So voltage divider formula gives me this, and this times Vi is equal to that. And then the transfer function, or the frequency response, is just the ratio of V out over V in. And then it will be this quantity over here, which is 1 over j omega c over R plus 1 over j omega c. But this form looks ugly. It looks very ugly, right? So how do I simplify it? I'll multiply numerator and denominator by j omega c. I get 1 in the numerator. I get 1 over j omega rc plus 1. Okay, if I just multiply numerator and denominator by j omega c. I get that. And that is my frequency response. Okay? And you are often asked to plot the frequency response as a function of frequency. And you're asked to plot this angle in space as well. So oftentimes you write the frequency response in this manner in terms of magnitude and phase. Okay? Then the magnitude of this frequency response would just be equal to the magnitude of this. And if you remember how to find the magnitude of this, it would be equal to omega squared r squared c squared plus 1 divided by this. Okay? And then how would you find this phase? Theta is also called the angle of h omega, and in some mathematical book it will be argument of h of omega. Okay, all different kinds of notations are used, they just mean the phase. And this quantity would be given by what? How would I find the phase? Given that this is the, it's not in the Cartesian form, right? So it puzzles you a little bit. So it's better to convert it into the Cartesian form. But actually you don't have to. If you have a complex number, z, and if you know its reciprocal value, okay, if I express this in terms of polar form, and then if I express this also in polar form, okay, how are the two phases related? Okay, the phase of something in the denominator is the same as the negative of the phase of something in the numerator. So I don't have to worry about reciprocating it to convert it into the Cartesian form. I'll just find the phase of the denominator. So what is the phase of the denominator? Okay, what is the phase of the denominator? How would I find that? I give you a hint. You do something with tangent. Okay, do you do something with tangent or arctangent? What?
Arctangent of JRC over 1.
Not quite correct. Not JRC over 1, but what should it be?
Oh,
Your Lee, right? Kyung Lee or something. He Young Lee, or maybe I got your name wrong. Or you pretend not to know your name today. So arctangent of what?
omega RC.
Omega RC over 1, right? That is the phase of the denominator, omega RC over 1. But then I have to put this there to make it correct. But since I'm finding the phase of the denominator, I put the negative sign to get this to be correct. The phase of the denominator becomes negative of the phase of the numerator. Okay? So this is the phase of that function, and this is just one way to do that. Okay? And you can plot this thing out. It will look something like that. That when omega is very small, it peaks. If omega is very small, it has a peak, and if I plot this, it will look something like this. But what happens if I plot this? When omega is positive, what angle does it give me? Say omega tending to infinity. Okay, omega tending to infinity. When omega is very, very large, what is the arctangent of something that is infinitely large?
Pi.
Pi over 2. Okay, but I have a negative sign there. So when omega tends to be very large, I have this asymptote of negative pi over 2. And similarly, if omega goes in the negative direction, I have the other asymptote, plus pi over 2. So the phase will look something like this. Okay? The phase relationship will look something like this for this plot.